Hello, everyone. Great to see that so many of you made their way back from the coffee break. It's my pleasure to spend the next 25 minutes, 30 minutes with you all talking about designing mixed reality games for kids with autism. My name is Mark, and I'm a senior product designer at Alva Labs, where we build digital tools to improve hiring processes and make them fairer and more efficient. But that's not really why I'm here today. In 2019, I decided that I need to take a break from my daily habits and break out of the design position that I had back in the days. And I wanted to learn something new and see something different. So I grabbed some stuff, threw it in a backpack, and I moved to Barcelona. Not only for the sun, the beaches, and the tapas, but also to pursue a master degree in what's called cognitive systems and interactive media. And as part of this study program, I've been working with the Full Body Interaction Lab at that university, which is a research group at that place. And together with a PhD student, a 3D modeling student, and the head of the research group, we continued the group's efforts in building games for kids with autism. And today I want to run you through the different approaches and methods that I found very handy when we were designing this and that I encountered and learned about. And show them to you. But I want to start by taking a closer look at autism first. So for that, I want you to imagine the following scenario. Imagine you're regularly commuting to your workplace using the local bus. And one day, as you are waiting at the bus stop, you notice another person that's sitting next to you that seems to be waiting for the same bus as you. And you realize that that exact person has been sitting there the day before as well. And as the next day comes along, you walk up to the bus station, and you see that same person sitting there again. This time, this person makes eye contact with you and starts greeting you. How would you react to this? Well, most neurotypical persons would engage in some sort of verbal or nonverbal greeting, since it's considered rude to not at least acknowledge the other person sitting there. Individuals affected by autism, however, they struggle with exactly these social interactions. Generally speaking, autism represents a pervasive spectrum of neurodevelopmental conditions. It has a highly heterogeneous phenotype, which means there's a great variety in its degrees of occurrence. That's why it's often referred to as autism spectrum disorder, or ASD. Even though it's so diverse, there are certain characteristics which are particularly common within individuals on the spectrum, which might be that they show repetitive or restrictive behaviors, that they have rather focused areas of interest, but they're also outstandingly good at deducting logic or identifying patterns, which makes them awesome gamers. One thing they, however, struggle with are the conventions imposed by society, and this can mean that they fail to initiate or respond to social interactions, that they interpret words over literal, or that they misunderstand or misinterpret certain context. And this is something that you can see already early on in childhood. And even though they can learn to respond to these social interactions, they're less likely to initiate them themselves, especially in spontaneous situations, like our bus stop example. So as a result, individuals on the spectrum often perform rather poorly on collaborative tasks. They might encounter overall compromised social interactions, which can eventually even lead to social fragmentation. And this can have an impact on various levels, from friendships to relationships, from financial to social dependence on family or caretakers, which eventually limits their self-determination and self-realization. To improve your social behaviors, research found out that you actually need to increase the amount of social interactions that you're having on a day-to-day basis, which is not really an enlightening surprise. It's more the no mastery without practice, right? So in consequence, researchers have been dedicating their efforts to develop training sessions for social initiations, something they call interventions. And I'm going to run you through a bit of the last decades of research, what people tried out, to present that to you. So they tried different things, and one first thing that they encountered was that when they start interventions early in life, meaning they have children in these sessions rather than grown-ups, they tend to be more successful and have a greater impact on the life quality of that individual. Then somebody came up with the idea, why don't we make this more fun and try something like game-based intervention, so having them engage with, for example, Legos, which is a huge successful intervention and probably the most used today. And as time passes by, somebody remembered, hey, kids on the spectrum, they actually love technology, so why don't we try something like playing with digital Legos? And there are a couple of different versions of that out there already, which I'm going to present to you in a minute. But when we started designing our tool, we looked at all of these interventions that are out there and tried to deduct common design patterns that have to be proven successful within these interventions, especially for applications for users on the spectrum. And there were 4 major principles that we identified from there. The first one is slow motion. Since fast animations or loud sounds can actually trigger fear or lead to a freezing reaction in individuals on the spectrum. The second one being consistency and predictability. So having clear rules doesn't mean they have to be easy, they can be difficult, but having clear rules and foreseeable outcomes and sticking to them, so really applying them consistently throughout your application. Incremental complexity. So an intervention should start out with readily acceptable interactions, and then over time introduce more gradually complex interactions along the way. And the last one being tangible interactions. So if you give a child something tangible to hold on to, they realize that this helps them to channel their attention, and that acts as a cognitive offloader for them, which makes it easier to focus at the task at hand. We also identified 2 more principles that we wanted to add to our list to help us guide our design and development work, which weren't specifically for autism, but more on a social interventions level in general. The first one being encourage collaboration. So we really wanted to make sure that the game that we're building helps to create social situations where 2 individuals would interact with each other, and also that it would raise out the positivity of collaboration, so really provide or show the value of it, of the collaboration. And the last one being continuity. So interventions are more successful if you have the chance to use them over multiple sessions, over a longer time period, rather than just having a one-off solution that you do once and then that's it. So coming back to the research on interventions that I mentioned before, since I was working with the full body interaction lab, they wanted to give this their own spin and own twist, because they're very interested in looking at the natural ways of interaction, or what's called embodiment. So they came up with this fancy wording here: early game-based technology-enhanced intervention facilitating physical embodiment. Whew. So embodiment is basically about how we perceive and conceptualize the way around us. So how our body helps us to mediate that understanding of what's going on in our world. And one thing to build such an intervention, or one way to do it, is to use mixed reality. And let me show you why by introducing the first framework that I want to show, which is called the reality-virtuality continuum. It consists of 2 extremes. On the one hand side, we have real environments, such as this room that we're all in here today. And on the other hand, we have virtual environments, which are computer-generated representations of either real or imaginary environments. Although these are opposite poles, they're not mutually exclusive from each other, which means that we find a continuum between the 2. And that's what we often refer to as mixed reality. And you can also see where augmented reality falls into place within that, for example. And finding the right spot on this continuum really depends on the context and the goals of your application. All too often, we just pick the fanciest gadget that we have in our labs or on our tables, and we just start playing around this without really reflecting of, is that the right thing to do the job at hand? And let me give you a generic example to make this point very clear. So let's say we're trying to train a plane pilot. If we put a trainee into a real plane and just let them take off on their first ever session, that is probably not a good idea, and that might lead to consequences that we don't really want to imagine right now. If we go to the other end of the spectrum and look at virtual environments, so having an exclusively virtual space that the trainees can interact with, such as these flight simulators that you could play on your old Windows machines, you reduce the risk of failure, obviously, but at the same time, you might also be missing a bit of context of the cockpit itself. Where are the buttons? Where are they in a physical space? Are they further up on the right, further on the left? You're probably interacting with a mouse and a keyboard, which are not going to be the interactions that you're actually having in an airplane once you fly the real thing. So to train someone properly, you would likely end up somewhere in between these poles, like this all-sim flight simulator that you can see here, where parts of the interaction are in the physical space, like the buttons, the steering wheel, and other parts are simulated, like the virtual environment that you can see on the projection in the front. All right, enough of pilots. Let's take this back to social interventions. So we already know that putting a child on the spectrum at a bus stop to talk to a stranger to practice social interactions might also not be the best idea. So one example of what researchers came up with is what you can see on the right side here, an intervention called echoes. So together with this virtual body on the screen, kids can practice joint attention exercises like gaze or pointing. And this is also a great example of what embodiment means, that you can really focus on the interaction of your body, like pointing somewhere on the screen or looking somewhere on the screen, rather than having to move a mouse around. And it also gives the kids the chance to engage in repetitive behaviors that they might execute. Even though this is a good example for embodiment, it also comes with a pitfall that you're focused on the screen a lot. So we're trying to educate kids about social interactions, right, which are happening from human to human. And in this case, it's a human-to-screen interaction. So it might not be the perfect solution. So we might want to push this further to the center here as well, just as we saw with our flight simulator, to have the technology only mediating that social interactions and allow the kids to focus on the interactions between them, to be more aware of each other's gestures and actions. And this is a setup that my department came up with for the game called Lands of Fog, where two kids are playing in a 6x6 meter floor projected arena. And in this floor projected arena, in this virtual environment, you see a dense fog. And wherever the kids go, the fog would kind of like open up and they could see underneath. And there would be monsters following them around wherever they go. And when their monster comes closer to the monster of the other player, the monsters would start greeting each other and engaging in these social interactions, to give them an example and a cue of what that means. And if they would come even closer, the monsters would combine and create new creatures, so they could play together and create different versions of this. And this intervention proved to be pretty successful, actually. And yeah, the evaluations were really, really well so far. But it also came with a couple of biases or issues, like that the monsters were liked by male players more than by female players. And that you were playing along a fixed storyline. So kids were trying to open a treasure box where they needed to find separate keys, and then once the treasure box opens, the game is done, and there's nothing that you continue it. So when we're coming back at this continuity, that wasn't really given. So once you open the box, the game ends, and you need to start over again. So we wanted to bring in new elements there and improve this with our game design. But before we go into this, I want to show another framework that I found very helpful when designing for mixed reality. And to start out with, I want you to think about when you're working with a computer. You have usually an input device, which is your touchpad, right, or maybe a mouse. You have an output device, which is your display in front of you. And you can see a logical interface, which is usually the cursor that you see on your screen when you move your mouse around. And there's a mapping between the input device and the logical interface. And this mapping really influences your understanding of that space that you're interacting with. So if I move my mouse, for example, just a teeny tiny bit, and the cursor jumps from one side to the other side of the screen, that could give me the feeling that this virtual space that I'm interacting with is rather small and limited. On the opposite end, if I move my mouse a lot, and the cursor just moves a teeny tiny bit, I might get the impression that the space is actually huge that I'm interacting with. And this concept that I want to introduce to you is called virtual subjectiveness. And it's pretty much similar to what I just explained here, but for the extended reality space. And to give you an example, I want you to think about a virtual environment. Let's say we built this application where you sit in a forest, you're being placed in a forest, and you can look around this amazing forest. But the only thing that you can do is literally look around. And we give you one of these head-mounted displays that you can use. So we have a display as an output device and the head-mounted display as an input device where you can turn your head around. So if you look at this virtual subjectiveness, what it means is we have our user with this input device and the physical mobility of your head rotation. So usually humans can turn their head roughly 90 degrees to each side. And if we map this one-to-one, meaning that if you turn your head 90 degrees to the right, your viewpoint also turns 90 degrees to the right within that virtual forest. You might just feel like you yourself you're standing in this forest and you're just taking a look around and browse. But if we change that mapping, if we do a 1-to-2 mapping, for example, meaning that if I turn my head 90 degrees to the right, the viewpoint turns a 180 degrees. This experience changes drastically, and you might be closer to what an owl is experiencing when it's sitting in a forest. So even though the virtual environment stays exactly the same, the experience becomes completely different. So these design decisions have a great impact, and they need to be thought through. But enough of the theory right now, so let's look at what we actually built at the laboratory. So for our hardware setup, we were going with what I already introduced to you, what was used in Lands of Fog. So we had a 6x6 meter floor projection from 2 projectors that were mounted onto huge scaffolds on each side. We had some speakers on the floors that would be able to support sounds in the game, and the kids could walk around on this floor area just very freely. But since we identified some issues with the game design, we wanted to come up with our own game that we could play in this setup. And to do that, we were trying to first come up with a suitable game theme that we could base this on. And if we look at very common or popular themes for kids on the spectrum, you will find 3 major ones, which are dinosaurs, the universe, and mythical creatures. I think they're all pretty cool, but for our use case, the universe seemed to be ticking a lot of the boxes. And since it comes with a certain logic, like the laws of physics that we could rely on and use and apply for our games, it was seemingly neutral enough to not favor male users over female players. And it's abstract enough to use algorithmics to create limitless numbers of situations so that we can have this continuity rather than just having one fixed storyline. So our overall game line turned into co-creating a universe, which means that users should make progress through collaboration, and the more they collaborate, the richer the experience should become. And as I said before, subjectiveness is a critical part of this interaction and how we form understanding of our virtual environment. So we also use that concept here to be thoughtful of what we want this to be. So we have our 2 users that we have playing in this arena, and as an input device, we gave this custom tool that we created for them. And we wanted this to be pretty abstract. Since we're in space, we thought it should give them some sort of astronaut feeling, that they can use this tool to interact and manipulate things that they see in the virtual environment. But it shouldn't be anything concrete that implies a certain interaction per se. And since we wanted them to feel agency over what they're doing, we wanted to make sure that the mapping is a 1-to-1. They shouldn't go 1 meter to the right and all of a sudden their logical interface moves in the other direction. Like, we wanted them to understand that they can interact with things using this custom device that we created. And the logical interface itself was this stardust cloud that you can see here, which was sort of a magical energy that they would move around using their tool, and that would maybe spark lightnings towards the objects to give them an indication that they can use this to interact and manipulate the objects that they're seeing. Let me run you through a typical play session. So a play session would start out with projecting the circular arena. It's circular because what we wanted to avoid is that users get stuck in corners and edges. If you have a circular arena, the moment you reach the border or the end, it redirects the focus into the center of the platform. So we don't have the kids standing in a corner and just being frozen there. Rather, we wanted to encourage to come back into the center and start over again. And as the users enter the game arena, they're here represented by these squares, we would start opening up these particle pools that we called white holes. And they would have different colors. There would be 4 different colors here. And when a user steps on one of them, they would start emitting the particles and send them over to the other player, which could be seen as an invitation to come and play or as a gift to the other player. Once they were sent out, the white hole would close down, and then it would randomly reappear in a different location later on in the game. Over time, we would introduce random objects trespassing the game arena, like this comet that you can see here. And when a user gets close to that comet with their particles, they would together form a planet. And the kids would have the chance to create all sorts of planets based on the combinations of particles that they would carry. So if they have different colors or different amounts of particles, the planets would have different properties, like maybe have a moon or different shapes, different textures, different colors, maybe a torus. So that is where we brought in this algorithmic thought and tried to create like an infinite amount of combinations, basically. Eventually, we'll reach a point where two players are stepping on these white holes at the same time, which would lead them to emit the particles, and they would collide in the center between the two white holes. And here, it really depends, again, on the combination of these white holes of what will be triggered. Sometimes it would just be a visual effect, but sometimes we would create these, what we call stars, which have a certain set of orbits around it. And something that you can't see here, but what we had in the real game was placeholders, like circular placeholders on each of the orbits. And maybe you see where this is going. But when a player gets closer to a planet, their little stardust cloud that was following them around would start sending these lightnings towards the planet. But on their own, they wouldn't be strong enough to do anything. So they would need to collaborate with the second player to be able to move that planet around and move it through the game arena, and eventually drop it on one of these circular placeholders on the star. So the players would go around, collect their planets, put them on the orbits, and once all the orbits are filled, the solar system is complete and would implode and open up a black hole, which can take the players into the next level, where they would encounter, again, different white holes with different colors, which allow them to create new versions of the planets and collect more different shapes. There's a bit more to this, but this is the main idea that I wanted to convey here today about the game. But so far, so good. So once we actually built this and had this set up, we were wondering, does this actually work? Like, does that do what it is intended to do? And it is usually not a good idea to start testing with kids on the spectrum right away, since animations or sound can actually cause harm to them. So what you want to do instead is you want to test with neurotypical people first. But one thing that I realized, because we were testing with neurotypical kids, is that testing with kids in general is very different to testing with adults, which I didn't think was such a big thing. But whereas adults would probably follow any given procedure that you tell them, kids have no issue on adjusting the game rules or the rules that you give them to be able to play with their friends or to make this a bit more of a fun experience for themselves. So sometimes you need to be a bit more creative when you want to get feedback from them and learn from them. So here are some examples of the research methods that we used throughout our testing sessions. The first one is drawing analysis. So after the kids played, we actually asked them to prepare multiple drawings for us. And the tasks sounded pretty vague, like, can you draw how you played? Which is a very, very open statement, but that was on intention, since we wanted to later on then go and analyze what they actually drew on the picture and figure out what are central parts of their drawing, what are more peripheral parts, and what might be missing, so that we get an understanding of what did they enjoy, what stuck out to them that they kept in mind to actually draw this, and what did they completely forget about. And since we created this digital tool, we also had the chance to collect data. So we were actually tracking the position of the kids to create these little heat maps that you can see here, to understand where did they move, how much did they move, did they actually just cover the whole game area, or did they just stay rather static in one space, and which elements did they interact with. And we did this for both players in the couple, and then we could compare like how did one player move compared to the other player. And one interesting learning that we took from this was that over time that the intervention passed, you would actually see the physical distance between the kids reducing. So they would actually get physically closer over time. Finally, we felt ready to test this with kids on the spectrum, but that was the moment where COVID hit Spain and things came to a more or less abrupt standstill. So the data that we collected up to that point gave us a strong indication that we're on to building a sophisticated intervention. We also spoke to psychologists that were involved in other interventions before, and they had a really strong belief as well and faith in our tool that we're building. However, there were things left that we still wanted to optimize, like using more physiological parameters like heart rate to understand how is that impacted by the game, or also find better measurements on counting social interactions between the children in that game session. And since I left, there has been a couple of things happening in the lab. For example, the Catalan Minister of Research and Universities was actually visiting the lab and playing our game. And also a previous classmate of mine is taken the project further, or created like her own version of the project now, which is called the Pro-Social Project, which uses a lot of the game dynamics that I showed you today, but it's more focused on having kids learning to engage in group activities. All right, I know that was a lot for the last 20 minutes, so let me give you a quick recap of what we spoke about today. So first of all, autism is a spectrum, which often causes difficulties with conventions imposed by society, especially when it comes to communication and social interactions. We are always designing on a reality-virtuality continuum, so think about your goals before choosing your tech setup for your application. Key design principles when designing for individuals on the spectrum are consistency and predictability, tangible interactions, and slow motion. Design your user's virtual subjectiveness within your application with intention, and don't turn your users into owls by accident. And last but not least, testing with kids requires creativity. So think about what you want to know and find an unconventional way in which kids could naturally provide you the feedback that you're looking for. If this awoke your curiosity or I left you confused, I believe we have some minutes now for a quick Q&A session. But do not hesitate to reach out on LinkedIn and keep this conversation going even after the event. Thank you so much.
Thank you very much, Marc. So do we have any questions for Marc? Okay. See, everyone is a bit shy. Okay. Great. We do have one question. Okay.
Yeah, so no, everything was very interesting, and so the experiment showed up to be very quite effective on the kids that tried. But has it already, or will it find a more practical use, even sponsored by the Catalan government, or is it just for research? And then, yeah, so this is my question.
Yeah, great question. So what I've been presenting here is obviously coming more from the academia, so the research group that I was part of, which is very much early stage research. So it's not commercialized in any sense. It's maybe funded by the governments and other sponsors, but it happens in academia. So there's no industry behind that yet that takes this over. So the next step would be to probably bring this out to the market. But we're at a stage where we're still trying to understand what impact does that have, and does that actually have a better outcome than, for example, these Lego sessions that have been around for a couple of decades already. So we're still in this proving phase of showing that this is maybe a better solution compared to the Legos. But I guess if you saw the setup with this floor projection, this is also quite difficult to set up in a regular place. You can't bring this to a kid's home or to a school maybe. So we're also struggling with this a bit. But I think as technology advances, there might be different versions of this where we could use AR glasses that are coming more performant now to be an alternative to that setup. So there's probably a gap to commercialization that we still need to go through.